Find somewhere comfortable if you haven't already. You don't need to follow any of this closely. You don't need to hold on to the details or remember where we've been. Just let the words come and go the way sounds do when you're drifting. Nothing to do but rest here in the dark and let something vast and patient wash gently over you. Tonight we're going to travel somewhere very far away, not in any way that requires effort, just a slow, quiet journey to the edge of everything, to places in the universe so still, so deep that even light cannot find its way out. And we're going to discover something strange and beautiful about those places, something that took one of the sharpest minds of the last century by surprise, something that changes, in a quiet way, how you might think about darkness itself. You don't need to concentrate. You don't need to understand every word. If you drift somewhere along the way, that's exactly where you're supposed to be. This is a story you can hear with your eyes closed and your body heavy, and it will still find you. So let the day recede a little. Let the weight of it settle down into the mattress beneath you. We'll begin gently and we'll go slowly, and by the time we arrive at the end of this, if you're still here, the night will feel a little softer, a little wider, a little more full of quiet wonder. There are places in the universe where the ordinary rules of things simply stop. Not where they bend or stretch or become hard to follow, but where they genuinely end, the way a path ends at a cliff, the way a sentence ends at silence. These are the places we call black holes, and for most of the history of human thought, we imagined them as objects of pure consumption. Mouths that swallowed everything and gave nothing back. Dark beyond dark. Silent beyond silent. But there is another way to think about them, and it's the one we'll carry tonight. Think of a shoreline. Not a turbulent one, a calm one, at the very end of a still day when the light is almost gone and the water barely moves. There is a boundary there, between the land and the sea, that is neither one thing nor the other. If you stand at it, you are in both worlds and neither. Step one way, and you are on solid ground, connected to everything familiar. Step the other, and you are carried away from it into something deeper and older and utterly indifferent to your intentions. The edge of a black hole is something like that. It's called the event horizon, and it is not a wall, not a surface you could touch or see. It is simply a boundary, a line in the fabric of space beyond which the pull of gravity has become so overwhelming that nothing, not even light, can turn around and come back. Cross it, and the universe you knew becomes, in a very real sense, unreachable. Not because of distance, because of the nature of the place itself. And yet, for all of that, a black hole is extraordinarily quiet. There is no fire at the edge, no roaring, nothing you could hear or feel as you approached. From the outside, looking in, a black hole is simply an absence. A region where the stars behind it are bent and warped into rings and arcs by the sheer weight of the thing, and where the center is just dark. It is this quality, the stillness, the consuming silence, that made what Stephen Hawking discovered in the early 1970s so astonishing. Hawking was in his early 30s then. Already he was living with a disease that was slowly taking away his body's ability to move, and already he had learned to do physics in a way that most people never manage, entirely in his head, without writing, without the crutch of a blackboard covered in working. He would lie still and think, and the mathematics would arrange itself in his imagination with a kind of precision that colleagues who knew him described as almost frightening in its clarity. He was working in Cambridge in those years, thinking carefully about black holes, about what they were, what they did, what the rules were that governed them. And he was doing this in conversation with ideas from another part of physics entirely, because in the 1970s something was becoming clear to a small group of theorists, that black holes, those supposedly simple objects defined only by their mass and their spin and whether they carried any electrical charge, were connected in deep and surprising ways to the laws of heat and temperature and the slow drift of energy from ordered things toward disordered ones. A physicist named Jacob Bekenstein had already suggested a few years earlier that a black hole has something called entropy, a measure of how disordered or hidden its internal state is. This was considered a strange idea, because entropy is a concept that belongs to steam engines and warm rooms and ice melting in a glass of water. What could it possibly mean for a black hole? And if a black hole has entropy, does it also have a temperature? And if it has a temperature, does it glow? Hawking set out to show that Bekenstein's idea was probably wrong. That was his intention, and what he found instead changed everything. The calculation he performed, carefully, over months, checking and rechecking, reluctant to believe his own result, told him that black holes do have a temperature, that they are not perfectly cold, not perfectly dark, that they radiate ever so faintly, like a dying ember in a vast and lightless room. That they are, in their own patient and almost imperceptible way, giving something back. He didn't believe it at first. He looked for the mistake. He went over the steps again. He spoke to colleagues and asked them to find the error. And slowly, quietly, the conclusion settled around him like a certainty. The most consuming things in the universe were, very slowly, losing themselves to the dark. The question was how. What was the mechanism? What was actually happening at that still and distant shoreline that allowed something to escape? To understand that, we have to go somewhere even stranger, somewhere smaller than anything you can picture, to the very texture of empty space itself. When you look at the space between things, the gap between your hand and the wall, the distance between stars, the void between galaxies, it seems, understandably, like nothing, like the absence of anything, like a container that happens to be empty, waiting patiently for something to fill it. But it isn't. At the very smallest scales, scales so fine they make atoms look like planets, the vacuum of space is not quiet at all. It trembles, it flickers. It is, in a way that takes some sitting with, alive with a kind of restless, ceaseless activity that never stops, not even for an instant, not even in the coldest and most remote corner of the universe. Here is what is happening there. Physics, at its deepest level, has a rule, a genuine, unavoidable rule built into the structure of reality. That says you cannot know everything about a particle at the same time. The more precisely you pin down where something is, the less you can know about how much energy it carries, and vice versa. This isn't a failure of measurement. It isn't that our instruments aren't good enough. It is simply how the universe is arranged, at the very bottom of things. And one of the consequences of this rule is that even in completely empty space, energy is never perfectly, precisely zero. It can't be. To be perfectly zero would be to be perfectly known, and that is not permitted. So instead, the energy of empty space fluctuates constantly in tiny ripples and trembles like the surface of a calm ocean that, looked at closely enough, is never actually still. These fluctuations do something remarkable. They allow pairs of particles to appear, to genuinely exist, briefly, borrowing energy from the vacuum for an instant, so short it borders on the meaningless. A particle and its mirror image, its opposite, its partner, flicker into being together. And then, almost before they have arrived, they find each other again and vanish, returning what they borrowed, cancelling each other out completely. The vacuum is repaid. The books balance. The space is empty again. This is happening everywhere, all the time, in the air around you right now, in the space between the atoms of your pillow, in the vast dark between galaxies, in the silence between stars. Pairs of particles appearing and disappearing, borrowing and returning, like tiny transactions so fast and so small they leave no trace on anything at the scale we inhabit. You might think of it like this. Imagine a still pond, and imagine that just below the surface, tiny bubbles are constantly forming and dissolving, appearing for a moment, then gone. From a distance, the pond looks perfectly flat. But the surface is never truly at rest. There is always something happening just below the threshold of what you can see. The physicist name for all of this activity is the quantum vacuum, and it is one of the most tested and verified ideas in all of science. The effects of this constant flickering have been measured in laboratories with extraordinary precision. The force between two metal plates held very close together in a near-perfect vacuum, a gentle, measurable push caused by the difference in vacuum activity inside and outside the gap, has been confirmed repeatedly. The vacuum is real. The flickering is real. The flickering is real. Now, in ordinary circumstances, all of this activity goes nowhere. The pairs appear, they vanish, the energy returns to where it came from. It is a closed loop, a self-contained trembling with no lasting consequence. But there is one circumstance under which the loop does not close. One situation in which a pair of particles appears, and before they can find each other and cancel, something intervenes, something vast and patient and utterly indifferent to the small drama playing out at its edge. A black hole. And this is where the story becomes something you might carry with you into sleep, not as a puzzle to be solved, but as an image to rest inside. Because what happens at the edge of a black hole, when one of those flickering pairs appears at exactly the wrong moment, or exactly the right one, is one of the quietest and most consequential things in the universe. Picture the event horizon, that calm, invisible shoreline, and picture the vacuum doing what it always does, everywhere, without pause. Pairs of particles flickering in and out of existence, appearing and vanishing, the universe quietly lending to itself and taking back. Most of these pairs appear and disappear without consequence. They arise in open space, far from anything, and they vanish again before the universe has time to notice them. But some of them appear very close to the edge, right at the boundary. One particle on one side, its partner on the other, separated by the thinnest imaginable margin. And when that happens, something changes. The black hole's gravity is not uniform near the event horizon. It pulls differently at different distances, a little stronger here, a little weaker there. And this difference in pull is enough, in some cases, to do something to a pair of particles that would otherwise have found each other and vanished. It can separate them. Think of two people walking together, close enough to reach out and hold hands. They are about to turn around and go back the way they came. But at the last moment, a door closes between them. One is on the near side, the other is on the far side, and the door cannot be opened again. The one on the far side, inside the horizon, beyond the boundary, is gone. Not immediately destroyed, but carried away by the geometry of that place, drawn inward along paths that lead only deeper. They no longer have a partner to cancel with. The debt that was supposed to be repaid has been, in a sense, forgiven by the black hole itself. That free particle, the one that escaped, moves outward into space. It is real now in a way it wasn't quite real before. It carries energy. It travels. If you were far enough away with a sensitive enough instrument, you could, in principle, detect it. This is the radiation that Hawking's calculation predicted. This is the quiet glow that black holes, all black holes, are always producing at their edges. But something else is happening at the same time, and this is the part that makes the whole picture so strange and so beautiful. When the particle that fell inward is captured, it brings with it something that, from the black hole's perspective, looks like negative energy, a kind of debt that the black hole itself has to absorb. The particle that escaped carried energy away. The black hole paid for it. Not in any dramatic way, not with a shudder or a flash. Silently, imperceptibly, like warmth leaving a stone on a cold night. You would not notice the stone changing. You would not see it happen. But if you came back centuries later, the stone would be cooler. And if you came back long enough after that, it would be cool all the way through. This is what a black hole does, moment by moment, across timescales that make the history of the universe seem like an afternoon. It loses itself, particle by particle, each one a tiny, silent transaction at the edge of everything. There is something in this that feels almost like generosity, not a deliberate generosity. Black holes are not conscious, not choosing, but structurally, in the way the physics works out, the most consuming things in the universe are also always giving something back. Not much, not quickly, but genuinely and without stopping. Hawking understood this in the early months of 1974, working through the calculation in his careful, unhurried way. And when the result became undeniable, when the mathematics settled into a clean and consistent picture, the first thing he felt, by his own account, was not triumph. It was something closer to wonder. The kind of quiet wonder you feel not when you've solved something, but when you've discovered that the world is stranger and more generous than you thought. So black holes glow, faintly, patiently, almost beyond imagination, but they glow. The next question is, how brightly? And the answer is one of the most counterintuitive things in all of physics, which is saying something, because physics at its depths is almost nothing but counterintuitive things. The relationship is this: the bigger the black hole, the colder it is. The smaller the black hole, the hotter. This feels wrong, the way many true things feel wrong before you've sat with them long enough. We tend to think of large things as warm, a big fire, a large sun, and small things as cool. But for black holes, it works the other way around entirely, and the reason has to do with the curvature of space near the edge. A very massive black hole has an event horizon so large that, near the edge, space is barely curved at all. The horizon is so vast, so gently rounded, that the difference in gravity between one side of a flickering particle pair and the other is almost nothing. The separation effect is extremely weak. The radiation it produces is correspondingly faint and cold. A small black hole, on the other hand, has a much more tightly curved horizon. The difference in gravity across the tiny gap between a particle pair is enormous. The separation effect is powerful. The radiation is brighter and hotter. Think of it this way. Imagine trying to tear a piece of paper by pulling both ends very gently. The paper barely feels the difference in force across its width. Now fold the paper many times until it's tiny and try again. The same pull now acts across a much smaller distance, and the difference in force across the paper's width is much greater. It tears easily. The smaller the black hole, the more violently the vacuum is being tugged at its edge, and the more energetic the particles that escape. For a black hole the mass of our sun, the temperature is so low that the number becomes almost meaningless, something like 60 billionths of a degree above the coldest temperature anything can possibly reach. Far, far colder than the faint background warmth left over from the universe's beginning, which itself is only a few degrees above that same coldest point. A stellar mass black hole is, in this sense, colder than the universe it sits in. It absorbs more from its surroundings than it emits. It is still net growing, for now. But a small black hole, one with the mass of a large mountain, if such a thing existed, would be a different story entirely. Its temperature would be high enough to emit real, measurable radiation. It would be losing mass at a rate that matters. It would be, right now, in the process of fading. There is a beautiful thought experiment here. Imagine a primordial black hole, one that formed in the first moments of the universe, when everything was dense and hot and chaotic, and tiny knots of matter collapsed under their own weight before anything like stars or galaxies existed. If such a black hole formed with just the right mass, it would have spent the entire age of the universe slowly evaporating, and it would be, right about now, approaching its final moments, glowing brighter as it shrank, getting hotter as it lost mass, the temperature rising as the size fell, in a feedback that accelerates toward the end. What the end looks like, we'll come to later. But hold for a moment the image of that ember, somewhere in the vast dark, if such objects exist. A point of warmth, patient and ancient, slowly brightening over billions of years toward a last quiet release. Present, unhurried, almost invisible against the enormous darkness around it. This is the temperature that Hawking's calculation revealed. Not a temperature you could feel, not a warmth you could hold your hands toward, but a real temperature written into the mathematics of the universe, present in every black hole that has ever formed or will ever form. A signature, a reminder that even in the most consuming silence, something is always gently escaping. It is very difficult to feel deep time. We understand it intellectually. We know that the Earth is old, that the universe is older, that stars are born and die on timescales that make human history look like a single breath. But knowing this and feeling it are two very different things. So let's try, gently, not to calculate, but to feel the patience of what Hawking discovered. A black hole, the mass of our sun, not the largest kind, not the smallest, just a modest stellar remnant, would take something like 10 to the power of 67 years to evaporate completely. That number is so large that it resists ordinary comparison. The universe has existed for roughly 14 billion years. Write that as a number, 14 followed by 9 zeros. Now imagine multiplying that number by itself and then by itself again and continuing until you've done it many times over. You are still not close to 10 to the power of 67. The gap between the age of the universe and the evaporation time of a single solar mass black hole is itself almost incomprehensible. Let's approach it from a different direction. Think of geological time, the slow drift of continents across the face of the Earth, moving at roughly the speed your fingernails grow, taking hundreds of millions of years to rearrange themselves into the shapes we recognize from maps. The Atlantic Ocean, widening by a few centimeters each year, will take hundreds of millions of years more to reach its greatest width before the slow dance of plates closes it again. That span of time, vast enough to feel almost abstract, is still just a brief moment compared to the life of a black hole. Think of the cooling of stars. Our sun, when it reaches the end of its life in about 5 billion years, will swell into a red giant, then shed its outer layers and leave behind a dense, cooling remnant. A white dwarf, slowly radiating its stored heat into space over hundreds of billions of years. Long after the last star in the universe has died, long after every galaxy has gone dark, that cooling will still be happening, very slowly, in the deep quiet of a universe with no new light in it. And even then, the black holes will still be there, barely changed, barely begun. It is only after all of that, after the stars are gone, after the galaxies have dispersed, after the universe has become a sparse and ancient and almost featureless place, that the slow evaporation of black holes begins to matter. In that era, the black holes are the last significant structures remaining. Everything else has faded, and the black holes sit there, patient as they have always been, losing mass so slowly that the rate is almost nothing, but losing it nonetheless. And then, eventually, a black hole reaches the end. As a black hole loses mass, it gets smaller, and as it gets smaller, its temperature rises, and as its temperature rises, it radiates more intensely, which means it loses mass faster, which means it gets smaller faster, which means the temperature rises faster. A slow cascade that, after an almost eternal patience, becomes a rush. The final moments of a black hole's life are very different from the billions upon billions of years that came before, where the evaporation was once imperceptible. It becomes, in the last fractions of a second, extremely bright. The temperature at the end is enormous. The energy released in those final moments is real and detectable and concentrated into a brief, brilliant flash. And then there is nothing where the black hole was. No remnant, no scar, just space. Slightly warmer for a moment, then not even that. There is something quietly moving about this image. The most patient things in the universe, the structures that outlast everything else, and not in silence, but in a brief and brilliant brightness. As though, after all that time, after all that stillness, they have one last thing to give before they go. The stone, finally, has given all its warmth to the cold night around it, and the night is just barely warmer for it. Hawking's discovery of the radiation that bears his name was, in itself, a resolution, a beautiful answer to the question of whether black holes have a temperature. But it opened another question, deeper and stranger, that would occupy him for the rest of his life and continues to occupy physicists today. The question is this: what happens to information? Information, in the physicist's sense, doesn't mean words or memories or the contents of a library. It means something more fundamental, the complete record of the state of a physical system. Every particle in the universe has properties, its position, its speed, its spin, the way it is connected to other particles. All of these properties together constitute the information of that particle, and physics, at its deepest level, insists that this information cannot simply vanish. It can be scrambled, hidden, transformed into something unrecognizable. Now consider what happens when something falls into a black hole. A book, say, or a star, or a single atom. As it crosses the event horizon, its information, the complete record of what it was and how it was arranged, is, in some sense, lost to the outside universe. We can no longer observe it. We cannot retrieve it. It is behind the door that does not open. In the era before Hawking's discovery, this was unsettling, but perhaps manageable. Black holes were eternal. The information was gone from our reach, but it was still there, somewhere inside, preserved in whatever form things take beyond the horizon. The universe still remembered, even if we couldn't ask it to show us. But Hawking radiation changes everything. Because if a black hole slowly evaporates, if it loses mass and eventually disappears entirely, then the information that fell in must have gone somewhere. And Hawking's original calculation suggested that the radiation coming out was completely random, carrying no trace of what went in. The information, it seemed, was simply gone. This was deeply troubling, not just philosophically, but mathematically. It meant that a fundamental principle, one that holds across every other domain of physics, from the behavior of atoms to the spread of heat, was being violated. The universe was, apparently, forgetting. Hawking believed this for a long time. He believed it, and he defended it, and he made a famous bet about it with another physicist in the 1990s, a bet that became one of the more colorful footnotes in the history of science, involving a baseball encyclopedia and a public concession that did not come easily. The concession came in 2004 at a conference in Dublin. Hawking stood up, by then communicating through his speech synthesizer, his body almost entirely still, and announced that he had changed his mind, that he now believed information was not lost, that it escaped somehow, encoded in the radiation that the black hole emitted over its long lifetime, that the universe did not forget. The audience was surprised. Some were unconvinced. The question of how the information escapes, what mechanism carries it, how it could be encoded in radiation that his own calculations said was random, remained unanswered. The concession was not a proof. It was a change of conviction, arrived at through decades of thinking. The work continues. Some researchers have explored the idea that the event horizon itself carries a kind of faint impression of everything that ever crossed it. Not a record you could read easily, but a subtle pattern, the way a shoreline holds the shapes of the waves that have washed over it. Others have suggested that the connections between particles, the deep quantum links that persist even across great distances, might be the channel through which information finds its way out, woven into the correlations between the particles of Hawking radiation in ways too subtle to see without knowing what to look for. Malcolm Perry and Sasha Hacko, working in Cambridge in the years before and after Hawking's death in 2018, continued to develop one particular thread of this idea, that the horizon accumulates something like a memory of every particle that has ever passed through, carried by particles that have no energy and leave no obvious trace, but that together encode the history of everything that fell in. It is not settled. It may not be settled for a very long time. But there is something gentle in the image it offers, the event horizon as a kind of patient record keeper, holding the story of everything it has consumed, not discarding it, but keeping it in a language too quiet for us to read yet. Even the most consuming things, it turns out, might be listening. No telescope we have built, or are likely to build in any foreseeable time, could detect the actual glow of a real black hole's evaporation. The signal is too faint. For a black hole of any mass we have found in the universe, the radiation is so cold and so sparse that it is completely overwhelmed by everything else. The faint background warmth of the cosmos, the light of distant galaxies, the noise of instruments themselves. We are, in this sense, deaf to the thing we most want to hear. And so physicists have done something quietly ingenious. They have built black holes of their own, not real ones, nothing that would consume anything, but systems that behave in the relevant ways exactly like black holes, systems that have a boundary inside which something cannot escape and outside which it can, systems where the mathematics of what happens at that boundary is, in the ways that matter, identical to the mathematics of an event horizon. The key insight is this. Hawking's calculation did not depend, in its deepest sense, on the specific details of black holes. It depended on the existence of a boundary, any boundary, beyond which things could not return. The physics that produces the radiation is the physics of boundaries and quantum fluctuations, and those can be recreated in a laboratory at human scales with materials that can be cooled and controlled and measured. One approach uses a cloud of atoms cooled to temperatures so close to absolute zero, the coldest anything can possibly be, that the atoms behave in a remarkable way. They stop acting like individual particles and begin to act like a single, coherent whole. A kind of quantum fluid moving together, responding together, responding together. Physicists call this state a Bose. Einstein condensate, named for the two theorists who predicted it, but the name matters less than the image. A cloud of atoms so cold they have, in a sense, merged into one. Inside this quantum fluid, ripples can travel, waves of density, like sound waves in ordinary air, and by carefully adjusting the flow of the fluid, physicists can create a region where those ripples cannot travel fast enough to escape. A region where, from the perspective of the ripples, there is a horizon, a boundary they cannot cross back over. At that boundary, the mathematics says, something very like Hawking radiation should appear. Not particles of light, but tiny fluctuations in the quantum state of the fluid, ripples that appear in pairs, one on each side of the boundary, separated and carried apart, just as the particle pairs are separated at a real event horizon. Jeff Steinhauer, a physicist at the Technion in Israel, spent years building and refining one of these systems. The work was meticulous and slow. Cooling atoms to the required temperature requires extraordinary care. Maintaining the conditions long enough to measure anything meaningful requires patience and precision that borders on the obsessive. In 2021, his team reported something remarkable. They had observed in their quantum fluid exactly the kind of fluctuations that Hawking's theory predicts. Not approximately, not suggestively. The measurements matched the theoretical expectation with a closeness that made the result difficult to dismiss. The pairs of fluctuations on either side of the boundary were connected, entangled, in the physicist's language, in exactly the way that Hawking's radiation and its interior partner should be connected. It was not a black hole in a jar, but it was, in the ways that mattered, the same idea, the same physics. The same deep structure, recreated in a room, in a laboratory, in a cloud of atoms barely above the stillest temperature anything can reach. There is something worth sitting with in this image, an idea born from thinking about the most extreme and unreachable objects in the universe, objects millions of times the mass of our sun, warping space-time around them, swallowing everything that comes close. That idea, tested in a room, in a device you could walk up to and look at, in a cloud of atoms smaller than your fist. The universe, it turns out, repeats its deepest patterns at every scale. The same rules that govern the edge of a black hole also govern the edge of a cold quantum fluid in a laboratory in Haifa. The same mathematics that describes the most violent and consuming things in existence also describes a gentle, quiet experiment in a room where people work carefully and speak in low voices and measure things with extraordinary patience. Hawking radiation has never been seen from an actual black hole, but it has been heard in its quiet way in a room, in a jar of near stillness, in a cloud of atoms so cold they have become, briefly, something like one thing. That feels somehow like enough, like proof that the universe is consistent all the way down, that the rules hold even at the edge of everything. We began at a shoreline. That calm, still boundary between the ordinary world and something deeper, the event horizon, the edge beyond which the rules we know no longer apply. We've spent this night walking slowly toward it, understanding a little of what it is, what happens there, what the darkness on the other side holds. And now we return to it one last time, before the night carries us somewhere wordless. There is a strange comfort in what Hawking found, not the comfort of a problem solved or a fear removed, but something quieter than that, the comfort of knowing that even the most consuming things in the universe are not, in the end, purely consuming, that at the very edge of the greatest darkness, something is always escaping, something small, something real, something that carries a little of the energy of that vast, silent place out into the wider universe. Black holes are not generous in any way we would recognize. They do not choose to give. They do not soften. They are what they are. Regions of such profound gravity that nothing with mass or light can return from them, and yet, at their very edges, the universe finds a way. The vacuum flickers, as it always does, and the geometry of the place means that the transaction cannot always be completed. One particle stays, one goes free. Over time, over the kind of time that makes the history of the Earth feel like an afternoon, that makes the lifespan of stars feel like a moment. This process adds up. The black hole grows lighter. The universe grows by the tiniest imaginable amount, richer. And eventually, at the end of an almost unimaginable patience, there is a last brightening, a final release, and then the black hole is gone, not into nothing. Its energy has been returned, particle by particle, to the space around it. The universe received it back. The debt, however ancient, was repaid. There is something in this that feels, if you let it, like a kind of reassurance. Nothing lasts forever, not even the things that seem most permanent, most immovable, most absolute. The universe recycles everything, in the end, however long it takes. The matter in your body was once inside a star. The energy in that star was once part of the chaos of the universe's beginning, and even the black holes, those ancient, patient, silent things, will one day return what they hold to the space around them, slowly, gently, without announcement. The information paradox, still open, still alive in the work of physicists who think carefully in quiet rooms, asks whether the story is truly preserved. Whether everything that fell into the dark left some trace, some impression, some faint record that the radiation carries back into the world. We don't know yet. The universe, at its deepest level, insists that things are not simply lost, that the record persists even when we cannot read it, that the story continues even when we can no longer hear it. Hawking spent his life with these questions. He moved through the world in a body that grew increasingly still, and he explored ideas of almost limitless motion, the bending of space-time, the fate of information, the nature of the boundary between the known and the unknowable. He was not a serene figure, by all accounts. He had a sharp wit, and a deep stubbornness, and a willingness to be publicly, cheerfully wrong when the evidence demanded it. But there is something in the image of him, working in his mind, in the quiet of Cambridge, turning over the mathematics of the most extreme places in the universe, that feels tonight like a kind of companionship. Someone once thought carefully about the darkness, and found that it was not quite as dark as it seemed. The laboratory in Haifa, the quiet cloud of atoms cooled to near stillness, the careful measurements that matched the theory so well. These are their own kind of companionship. People working patiently, listening for the faintest possible signal, confirming that the universe is consistent and strange and full of things we have not yet fully understood. There is no urgency in that work. There is only attention and patience and the slow accumulation of understanding. You don't need to hold any of this. You don't need to carry it anywhere. The black holes will be there tomorrow and the next day, and for an almost unthinkable time after that, patient at the edges of galaxies, slowly, slowly giving back what the universe lent them. The shoreline is still there. The water barely moves. Somewhere beyond the horizon, something is always gently escaping. And so we leave it there. Somewhere behind you, the day is already distant. The questions can wait. The darkness is not as deep as it looks, and the universe is taking its time with everything, including you. Drift now, if you're ready.